Now they can hear us. What's up, Red Day class? All right. Here we go. Yeah, and the nice thing, it'll be posted to Canvas, so you can always review and laugh at everything you say. Okay. So you probably noticed in the AP quiz, it made reference to rolling without slipping. So there is a difference to rolling without slipping versus rolling with slipping. And we need to conceptually know what the difference is between the two. So without slipping, this is an application of kinetic energy. So we could say that if I'm rolling without slipping, so like if a hoop rolls across the table, right, that my total kinetic energy is made up of two kinds, our normal kinetic energy and our K rotational. The word that AP likes to use instead of linear is translational. So this is translational kinetic energy, which also means linear. Okay. And that's our rotational. So two terms for the same thing. So my question is, can we relate translational motion to angular? In other words, is there a relationship between, say, how fast this is rolling and how fast it's moving that way? And if so, what is it? What do you think? Do any equations pop into mind that we've used before?
Isn't it like linear equals angular times radius?
Yeah. We had like delta x equals r delta theta. We had v equals omega r, or r omega, however you want to write it, and a equals alpha r. Right? So those all are true when we're not slipping, as long as we're not slipping. And we just add one little detail to it. For example, velocity, like how fast it's going, we're measuring the velocity of the center of mass of the hoop, not like a point on the outside or things like that. The center of the mass is where it is. So we would just add a little, like on our notes here, add center of mass to all of those. And then that would be true, that those things work, they relate like that, and everything's good. The situation changes when we roll with slipping. When we roll with slipping, we lose kinetic energy to friction as we roll. Which means that we cannot relate translational motion to angular. Because, for example, if this hoop slips, it doesn't go as far with each rotation, which means my center of mass didn't go as far as the rotation would say it does. Right? In other words, it's rotating, it's continuing to rotate, but not moving as far left and right as it normally would if it slips.
What do you mean by slipping?
So if we were to slip in place, it'd look like this. Right? So like we could make my hoop rotate, but not move.
So it's like rolling, but then it like does that.
Yeah, so it's rolling, but doing a little bit of this while it does.
Got it.
Right.
I thought it was like just rolling and then stops rolling and starts.
Well, eventually it will stop because we'll lose all of our energy to friction. Yeah. So one of the ways that AP likes to represent this is with graphs. So it might look something like this, where you could picture maybe a bike wheel, something like that, and it's rotating this way. So it's going to roll across the ground, We'll make it level ground so it's nice and easy. And then they like to make these energy graphs.
Wait, what's that W?
Yeah, omega. And then they might make a bar graph like saying, we start out with all of this kinetic energy. That's my total kinetic energy. And what type of energy is friction? What type of energy does it create? Heat. So the other type that we could have would be thermal energy. And as we just start, I wouldn't have generated any yet. But if we're slipping, eventually, like by the time I get to this other side here, I will have lost some of my kinetic energy. And the amount that I lost goes into thermal energy. So if we were to stack those two bars on top of each other, they'd be the same size as the original. Energy still conserved, but we're losing some to heat. And eventually our wheel comes to a stop when all of the energy is in the form of heat. Does that make some sense? So you'll see graphs like that depicting, like, where does energy go? And you'll get some more practice with that next class too. All right. So let's try a problem real quick. See if we can remember how to do these ones. So let's start without slipping. We have a 4 kilogram hoop with a radius of 0.5 meters rolling with a velocity of 2 meters per second. When it encounters a hill, if the hoop rolls without slipping, how high up the hill does it go? So conservation of energy, what type of energy am I starting with? Starting with kinetic energy. What types of kinetic energy? Rotational and translational, yeah. Translational. And then eventually, when it's up as far as it will go up the hill, it's in the form of potential.
How do you know it stops?
Because it would be at its max height. Kind of like throwing a ball up in the air. What's its velocity at the top? Yeah. So rotational is 1/2 I omega squared. Translational was 1/2 mv squared. And gravitational is mgh. We're going to see if we can remember our steps from doing this before. I for a hoop is mr squared. And do you remember what we substituted for omega in problems like this?
V over R.
Good, v over r. Plus 1/2 mv squared equals mgh. All my masses are going to cancel. The r squareds cancel. And all of a sudden things get a little simpler. We have 1/2 v squared plus 1/2 v squared equals gh. 1/2 plus 1/2. Oh. V squared equals gh. Go ahead and solve for h for me.
Do the M's on both sides cancel?
Yes, all of the m's cancel. So it's this r squared cancels with that. Oh, yeah. Because it's like r squared divided by r squared.
What is G? Yeah, I think it's like 9.8.
So that's squared with the r here. So it's like r squared divided by r squared.
Why did we ever change it to V over R?
Why do we or why?
Yeah.
Because usually we're looking at like how fast is it going this way, is a much easier measure. How fast it's spinning.
Okay.
So that's if it gave me like an angular velocity instead of a linear, then I might do the other way around.
Okay.
But usually that's not what happens. Yeah, good. So height, v squared over g. 2 meters per second squared divided by 9.8 meters per second squared, which gives us 4142. So both are fine. Yeah. Okay. If instead the hoop slips as it's rolling and we lose a total of 2 joules of energy as it rolls up the hill, how high does it make it now? So, to start, what type of energy do I have? And? Translational, yeah. Equals, well, I'm going up the hill, so I gain some potential energy. But what happened along the way? What else? Well, I created some heat. And conservation of energy is still true. If I add in the amount of heat I generated, we still have the same amount in both places. But by the time I get to max height, I've generated 2 joules of heat energy. So similar setup, 1/2 I omega squared, 1/2 mv squared, oops, not 1/2, mgh, and then just my thermal energy. That's where we'll put those 2 joules. Is any of the work going to be any different other than the 2 joules? No. So let's skip some steps here. V squared equals gh plus my 2 joules of thermal energy. So to solve for height, we have to do v squared minus the 2 joules divided by g. And if we put that into our calculator, what do we get? We got a number for me? Yeah, whatever 2 divided by 9.8 is. 0.2? Okay. Should be right around there. 0.2 meters, about half as much. Good. So that's the only way that AP would ever make you do this numerically, is they'd have to give you the amount of energy, since we don't have a way of calculating it. It's a little different than our like friction times normal force when it comes to stuff that's rolling. All right. Shifting gears now. Back to orbits. We talked about this a while ago when we did circular motion. We had Newton's universal gravitation and centripetal force and all that stuff. And at one point we kind of really casually threw out an equation for like gravitational potential energy, but on a like planet scale. And so it's time to come back to that a little bit. So we sort of threw out this one that gravitational potential energy could also be equal to negative G mm over R. And we set it to be negative in physics to show that it's what we would call bound. In other words, they're sort of like stuck together, right? So in order to be unstuck, you actually just have to get to 0 is the value you want. We do the same thing with like electrons in orbits, is we call their amount of energy 0, or call their amount of energy negative, to show that it's like stuck in this pattern, right, of going around in a circle. So the negative is there. We can kind of play with a little bit though when we go to calculations, and I'll show you what I mean. So we talked about circular orbits, right? That's where we lived before because we were talking about circular motion. In the case of circular orbits, my radius of my orbit stays constant. Therefore, my energy stays constant. So we could say that mechanical energy gravitational potential energy, because I'm going at a constant speed, we could also include angular momentum. Constant speed also means kinetic energy would stay the same. All remain constant. When we are in this nice fixed orbit that's a circle, everything stays the same because I'm always the same distance away from that, say, gravitational source that's causing the orbit. However, most orbits don't work like that. Some can be approximated that way, but not many. Most orbits are elliptical. So when I say an orbit's elliptical, what does that mean to you? Yeah, it's more of an oval shape, right? And we'll see a visual of that here in just a minute. But because it's an oval shape, what changes? The radius changes, right? Now, there's no outside work being done. So in terms of mechanical energy, is that going to stay the same? Yeah. Mechanical energy stays the same. And if there's no outside work being done, are there any outside torques that are acting on the system? No. Which means angular momentum is also constant. And we'll come back to that one in just a minute.
Wait, why is it constant?
Because there's no external torque on the system.
And why is the
Again, because there's no work being done, no outside forces, no outside torques. So it's a closed system, is what we would say. However, my kinetic energy and gravitational potential energy do change. Right? The amount of potential energy I have is dependent on radius. So as my radius gets bigger, gravitational potential energy changes. And kinetic energy will change exactly opposite, so that my total remains the same.
So does that mean like the planet like speeds up or slows down?
Yeah.
Is the Earth?
Exactly. The Earth is elliptical. Almost everything is elliptical. So let's take a look at what we mean here. So this is an example of an elliptical orbit. When we have an ellipse, remember we have two focus points. That's how an ellipse works. Whatever the source of gravity is, in this case the sun, is always at one of those. Right, so we have the sun there, and then just an empty one. And so what happens, I have it up there so that it shows you the speed as we go around. I don't know why the sound. I've never heard planets make that noise. I don't know. I'm going to turn that off because that's really annoying. So look at what's happening to the speed as we go around. As we come around this side, it's faster, slower, slowest, starts to speed up again. Right? And why does that happen? Yeah, my radius is decreasing. Right? My radius is decreasing, so gravitational potential energy goes down, kinetic energy goes up.
So when you circle the
Right?
nearest the Earth, you would think that's
When we are closest to the sun, which is not summer.
no. When is it?
So summer, remember, so we have the Earth is tilted. So summer is when that tilt in the northern hemisphere is closest to the sun, right? Which doesn't necessarily line up with when we are closest. But it turns out like the amount of heat that we get from the sun doesn't change much from our closest to furthest parts of the orbit. So I'd have to look. I don't remember the dates. We'll have to look. It's called perigee and apogee, are the closest and furthest.
What is like the little blue X?
So those are the two. When you have an ellipse, you have two like focus points. The two X's represent those. It has to do with a geometric part of it. The way I can show you if we do, it's called put strings on it. So the distance it is away from the two. If you add these distances together, it's always constant. And so those are just the points that basically make that true.
Is it like another planet, or is it just like?
It's just empty. Yeah. Yeah, it literally is an empty point in space. Yeah.
How elliptical is
The Earth? Let's see. So if we change it, if we go try and match the Earth orbit, it would look like that. And so that means we'd have to decrease this to like something like that-ish. Right, not perfect. It is close-ish to circular, but not entirely. It does have two focus points still, yeah. Yeah, and at this scale is kind of hard to see too. All right. So that's what happens when we have an elliptical orbit. From AP's perspective, the big thing is to know that we're going to have this change between kinetic and potential, that they're going to kind of go back and forth. Think about like we use the, remember the skateboard thing? Whereas like it kept going back and forth between potential and kinetic. It's kind of like that with orbit, right? We're going to be going back and forth between those two things, but my total is always going to remain the same. So as long as we know mechanical energy and angular momentum are constant, those things change. That's what we need to know. Which brings us to the more fun part, which is escape velocity. So the definition of it is kind of weird. This is the velocity needed to make total mechanical energy 0. Because remember that potential energy we define as being negative. So it would be like saying that we have as much kinetic energy as we have gravitational potential energy. So in other words, more practically, this is the velocity needed to leave orbit without any additional work being done. Right? If something starts out with this velocity at some instant, it will leave orbit. Right? Which is a little different because a lot of times when we think about leaving orbit, what sort of things do you think about?
Natural.
How about like leaving Earth's orbit?
Natural.
Other way around. I want to go from Earth to gone. What am I going to get on? I'm going to get on a rocket.
Oh.
But as my rocket goes up, my rocket actually doesn't need this amount of escape velocity because what's happening constantly as the rocket's going up? Work is being done by the rockets. Yeah, by the engines of the rocket. So it's constantly adding velocity as it's going up. So this is a little different than that. This is a situation where I'm not adding any additional energy into the system.
How do you get to that velocity?
Doesn't matter.
So like,
Once you're there, you can leave orbit.
like it's like
Okay.
how fast will I have to run? Like
Yeah, that's maybe a good way to put it.
Actually,
Yeah, or like if I was gonna fire a cannon, this is how fast it would have to be going to leave completely.
Without like big cannon having like little engines and like.
Right, without constantly adding more to it.
So it's
Yeah,
not,
like the moment it leaves the cannon, it would have to have this velocity. Yeah.
So it's not like the entire object, like all of Earth leaving orbit. It's just something leaving orbit.
Yeah, something leaving orbit. Could be a golf ball. Right.
Yeah, I thought it was like how fast.
So how fast you have to hit a golf ball to send it to space, right? So we can actually figure out this number because we know kinetic energy minus gravitational, because remember it's negative, equals 0, right? That's what our definition said. We're moving fast enough so that we have 0 total energy, which means it's where my kinetic energy is equal to my gravitational potential. And kinetic energy is 1/2 mv squared. Gravitational potential is mgh. Oop, not mgh. Other gravitational potential this time. G m over r.
How do we know when to use which one?
If we're talking about space and orbits, you're using the GMM over r. That's really the only application to it.
Oh yeah.
Wait, it was negative up here,
Oh.
so up at the top there.
Yeah.
Yeah.
Our sheet in the test.
Yeah. Yep. Yeah.
So why G and R? Why is that not negative? Because we said it was negative.
It is negative right here.
Oh, okay. So
Yeah.
just when we move.
Yeah, right at the top there. Okay, we want to solve for velocity, like how fast we would have to go. So then I'd multiply by 2 and take the square root. So my escape velocity is the square root of 2gm over r. The mass here, that's the mass of, say, the planet or sun or whatever is being orbited.
Not the thing trying to leave.
It's not the thing trying to leave. Correct. That's the one we canceled out, yes. And then r, remember, is distance between centers of mass. So if we're on Earth, what's the r that we should use if we're on the surface of the Earth? Yeah, if I'm leaving Earth. Distance to the center of the Earth. Yeah. If I want to leave Earth, r is the distance to the center of the Earth.
But the mass would be the mass of the sun.
Mass of whatever is leaving. Or I'm sorry,
Yeah.
mass of the planet or star, whatever we're trying to leave. So let's do an example.
I'm a little confused.
Yeah, let's do an example. That'll make some sense. What is the escape velocity for planet Earth? So, escape velocity is square root g mass of the Earth and radius of the Earth.
Is this ever going to be on a test?
Yes.
Does this ever happen?
Oh yeah.
Like something goes fast and it.
Yeah, like a rock.
Oh yeah. One interesting case actually is helium. There's actually no helium or very, very little helium in our atmosphere because it's how fast it naturally moves is greater than the escape velocity for Earth. So it all ends up leaving the atmosphere, which means the only place we can find helium is places where it's trapped underground.
Because it moves so fast.
Because it moves so fast. So like if you let go of that helium balloon and it pops, all that helium goes off into space
Can they
eventually.
make helium?
It's no, not really. Not easily anyway.
Helium's like-
Not without
What
nuclear
if we
fusion.
run out of helium?
That would be bad.
Yeah.
No more birthday. But also keep in mind it gets used for other things that are actually probably more important, like MRI machines and CAT scans and
Is there a possibility that
things like that. So, anyway, yeah, that's the whole.
run out of helium?
We could, yeah. So, square root of 2, and what's g? Do you remember?
Oh, not 11.
Yeah, it's 6.67 times 10 to the negative 11.
So is this like a real concern for like
Is it a 7 or a 9?
Oh, 6.67, yes.
Is this like a concern like about the Earth running out of helium?
I mean, kind of. Not. We're not in a dire situation, but you know, it's there. Mass of the Earth. What is it? Well, enough you got computers up. Let's look it up. What's mass of the Earth? Yeah.
If like there's a concern of like if we could possibly lose the helium, then why do we use it for boost?
That's a great question.
Yeah.
Yeah, because like we need it for like
If I remember right, the answer that I heard to that is that the helium that gets used in MRI machines and stuff like that is a specific isotope of helium. That's not necessarily what you would put into a balloon.
So where does it
But I can't remember that for sure.
Where do you guys find it? Like in
Underground.
caves?
Underground, usually
Like,
with
if you, like,
usually
put it
actually where they
in,
find
like, a pocket,
where they'll find like oil and stuff, where there's like pockets of oil actually above that.
is it
Sometimes
just,
there's trapped
like,
helium.
just like a
Yeah.
gap?
5.97 times 10 to the 24th.
How do they collect it? Do they keep a big balloon
Do they just, yeah.
I mean, kind of.
Wait, really?
I mean, not necessarily a balloon, but some sort of container. I don't know the process that well,
Like
but
a Tupperware?
you know, 10 to the 24th. And then radius of the Earth in meters.
Do you do it to the, how can you do it to the surface of the earth? Is it weaving from the surface of the earth?
Exactly.
3,963. Oh, that's miles.
Miles is no good. Meters.
6.38 million.
Okay, 6.38 times 10 to the 6th meters. Great. See if you can remember scientific notation on your calculator. Let's throw something in there.
Right, let me check.
Wait, I'm really worried about this helium.
Yeah. No more birthday parties.
Now, this is one of those cases where sometimes knowing physics takes the fun out of things.
Yeah, it really does.
Now all of a sudden your view of birthday parties
There's
is...
a button in space.
Yeah, that makes
Well,
sense.
and how are you going to get it from space? Sounds expensive.
Yeah.
How do I put it in a scientific notation?
Remember the double E button?
Yeah, but how do I put it from my
What
answers?
happens if we run out of it, and are we running out?
Can I just guess?
Well, I mean, we said that I'm sure that they can go back. Well, isn't it about negative
And times 2.
We get to use that for the radius.
Oh, yeah, it's like we're using like an average radius.
Yeah, because
You're like, what if I was standing on a mountain?
I found that out the other day. And
Yeah,
it broke.
it's kind of squished in the middle.
It's literally just a lump.
Yeah.
It's just a lump of rock.
Is it?
It's not perfectly
Because
circular.
it's just
Okay. It's like that.
Wow, that definitely.
Okay.
11172.
So we don't have any to use. What do you got?
11172.
Yeah, 1,172.6
I wonder if we can figure out
meters
how to
per
make
second.
helium if you can make a bunch of money.
Well, you can if you use nuclear fusion. That's the only way to do it. That's what happens inside the sun. We fuse hydrogen to make helium. Okay, so there's our escape velocity. If you need individual help on calculations, we can do that later. But there's some fun applications to this.
I forgot to take the square root.
Yeah, I got 11,106.
Oh, that's why.
Oh.
I didn't start it.
Okay.
Just a little calculator error somewhere.
That's
Isn't
silly.
it? Isn't there?
Did you get enough?
Yeah, I did.
Okay.
2ISM.
Yeah,
Yep.
I have 3 ones.
Yeah, I have 3 ones.
Yeah, I
Oh,
have
3 ones?
Yeah, I like ones.
Okay.
Oh, I thought I was using.
11,172.6.
Yeah, that's what I got.
Okay. Okay. All right. Double check.
I think that's not that
I feel like that's. I actually feel like that's too fast, but let's see.
No, that's what I got.
That's what I get for not calculating it ahead of time.
You're crazy.
9 times 10 to the 4th divided by 9.
This is what I got. That's why I did so. Exactly. So I'm like, I don't know.
Yeah. Okay. There we go.
So this is like.
So this would be like if something is like instantly going this fast, it has enough energy to leave orbit.
If I run that
So when I
fast,
go this fast, so if I'm like driving this fast down Parker Road.
Yeah, Jane just takes off. And goes. Yeah. Okay. One of the more interesting applications is this. Listen. A black hole.
Go on the bus.
So a black hole is an object where the escape velocity is higher than the speed of light. In other words, light cannot leave a black hole. So we can actually use that to figure out what's called the Schwarzschild radius of the black hole. So it's sort of like, this is the radius of the black hole where you wouldn't see anything anymore. Where all of a sudden it would look like things are gone. Yeah. So, start with this. We know that kinetic energy would have to equal gravitational potential to figure out our escape velocity. But this time, my speed is the speed of light, which we usually call c. So c squared equals g m over r. One of the masses cancels out. And this time we want to solve for r. Like, what's the radius? So see if you can do the algebra there.
1/2 or GM over 1/2 C squared.
Yeah, gm over 1/2 c squared, or usually it's written as 2gm over c squared. We just flip the fraction around. Yeah. Which is kind of cool that it's that simple. That's how you find the radius of a black hole.
Cool.
Yeah.
I'll keep that in mind.
Next time I.
So,
Next time I see it.
right?
So are like black holes something I should be like worried about?
Let's find out. So, using the above equation, let's find out how big a black hole would be if it was formed using the mass of the Earth. Like, if the Earth all of a sudden turned into a black hole, how big would that black hole be? So, R equals 2gm over c squared. So 2 times 6.67 times 10 to the negative 11th
How would that happen?
Newton meter squared per kilogram squared. We'll talk about that in just a second. Mass of the Earth. Well, you just did that in the previous one. What was that? 5.97. 7 times 10 to the 24th kilograms. The speed of light is 3 times 10 to the 8th meters per second.
That's not that fast.
Squared.
What does C stand for?
C is the speed of light.
Speed of sound or speed of
Speed of light is much faster.
Like why
The speed of sound in this room right now is around like 350 meters per second.
That's 10 to the 8.
How do you
And that's 10 to the 8th, yeah.
Okay, so I know like to think about like the speed of sound, I think about like, oh, how long will it take for my voice to reach your ear?
Yeah.
But like, how do you think about it like that in terms of like
Same thing.
how?
Is it how long? So if I'm looking at you, how long does the light that's reflecting off of you take to get to my eyes? Very little time. Light from the sun to get to the earth takes 8 minutes.
So we wouldn't know for 8 minutes.
Yeah, if the sun exploded, we wouldn't know for 8 minutes. Yeah. Anyway, what do we got for a radius here? So many fun things to talk about. 0. Point,
I don't know. I don't think that's right.
I don't know. Throw it out there. We'll see. I didn't actually calculate it.
0.0022.
But that's not a very big.
Wait, what?
Okay, maybe I was
I
wrong.
love 0.00.
I'll double check.
I thought 0.08.
Did you swear that I do it?
Yeah.
I haven't done it.
I got,
Oh, wait, no, I did it wrong.
yeah, I got something a little different.
Okay.
I got 0.008. All right,
I
so,
got 2.
yeah. Which is kind of crazy to think about. And this is how wild black holes are. In order to make a black hole out of the Earth, you'd have to take all of the mass of the Earth and put it down into a sphere that had a radius of, what, 8 millimeters? It would be
8 millimeters?
that big. All of the mass of the Earth
How
there.
the freak does that work?
And actually, technically, all of the mass of the Earth down to an infinite point. So that's how big the black hole would be. Right?
Or does it just like collapse? Go
Yeah, so the way this works, this wouldn't ever happen with a planet, ever, right? It normally happens with stars. Oh. Where did my other... Oh, did we miss a question? No, we didn't. No, we didn't. Okay. The way this normally happens with stars is it happens with stars that are hundreds of times bigger than the sun. Right? So we're already in pretty crazy territory, right? And what happens is there's two sort of things fighting each other in a star like that. There's gravity pulling stuff in, and there's this sort of heat and radiation pressure pushing things out. And there's kind of a nice balance to that when the star's working well. As it starts to fuse and use up all of its fuel, so hydrogen fuses into helium, and so on and so forth, makes, in a star that big, you'll make everything in the periodic table up to iron. And once you make iron, you can't have nuclear fusion anymore. That's the biggest element you can make by nuclear fusion. So once that happens, the star stops working.
why?
Because it can no longer fuse material, so it can't generate any heat. And so all of a sudden, those forces that are pushing outward don't exist anymore, which means gravity is the only thing that exists, and so it collapses in on
How
itself.
fast does that take?
For a long time.
Like a long time from a human perspective, instance from a universe perspective. A couple of years, which is really, really fast on a universe scale.
Are we done?
So, and then it's just how, so just like where the star was, it's just now flat.
Yeah. There'll be some material that's ejected in the process too, so you'll see some stuff come out. But yeah. All right.